During the history of deep learning, many researchers, including some very well-known researchers, sometimes propose optimization algorithms and show they work well in a few problems, but those optimization algorithms subsequently were shown not to really generalize that well to the wide range of neural networks you might want to train. So over time, I think the deep learning community actually developed some amount of skepticism about new optimization algorithms, and a lot of people felt that, gradient descent with momentum really works well. It was difficult to propose things that work much better. So RMSProp and the ADAM optimization algorithm, which we'll talk about in this video, is one of those rare algorithms that has really stood up and has been shown to work well across a wide range of deep learning architectures. So this is one of the algorithms that I wouldn't hesitate to recommend you try because many people have tried it and seen it work well on many problems. And the ADAM optimization algorithm is basically taking momentum and RMSProp and putting them together. So let's see how that works. To implement ADAM, you would initialize VDW equals 0, SDW equals 0, and similarly VDB, SDB equals 0. And then on iteration T, you would compute the derivatives, compute DW, DB using current mini-batch. So usually you do this with mini-batch gradient descent. And then you do the momentum exponentially weighted average. So VDW equals beta, but now I'm going to call this beta 1 to distinguish it from the hyperparameter beta 2 we'll use for the RMSProp portion of this. So this is exactly what we had when we're implementing momentum, except that I've now called the hyperparameter beta 1 instead of beta. And similarly, you'd have VDB as follows. So 1 minus beta 1 times dB. And then you do the RMSProp like update as well. So now you have a different hyperparameter beta 2 plus 1 minus beta 2 dW squared. Again, the squaring there is element-wise squaring of your derivatives dW. And then SDB is equal to this plus 1 minus beta 2 times dB. So this is the momentum-like update with hyperparameter beta 1, and this is the RMSProp-like update with hyperparameter beta 2. In the typical implementation of ADAM, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dW equals V dW divided by 1 minus beta 1 to the power of t if you've done t iterations. And similarly, V dB corrected equals V dB divided by 1 minus beta 1 to the power of t. And then similarly, you implement this bias correction on S as well. So that's SDW divided by 1 minus beta 2 to the t, and SDB corrected equals SDB divided by 1 minus beta 2 to the t. Finally, you perform the update. So W gets updated as W minus alpha times. So if we're just implementing momentum, you'd use VDW or maybe VDW corrected. But now we add in the RMSProp portion of this. So we're also going to divide by square root of SDW corrected plus epsilon. And similarly, B gets updated as a similar formula. VDB corrected divided by square root S corrected dB plus epsilon. And so this algorithm combines the effect of gradient descent with momentum together with gradient descent with RMSProp. And this is commonly used learning algorithm that's proven to be very effective for many different neural networks of a very wide variety of architectures. So this algorithm has a number of hyperparameters. The learning rate hyperparameter alpha is still important and usually needs to be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dW, right? This is the momentum-like term. The hyperparameter for beta 2, the authors of the ADAM paper, inventors the ADAM algorithm, recommend 0.999. Again, this is computing the moving weighted average of dW squared as well as dB squared. And then epsilon, the choice of epsilon doesn't matter very much, but the authors of the ADAM paper recommended 10 to the minus 8, but this parameter, you really don't need to set it, and it doesn't affect performance much at all. But when implementing ADAM, what people usually do is just use the default values of beta 1 and beta 2, as well as epsilon. I don't think anyone ever really tunes epsilon. And then try a range of values of alpha to see what works best. You could also tune beta 1 and beta 2, but it's not done that often among the practitioners I know. So where does the term ADAM come from? ADAM stands for Adaptive Moment Estimation. So beta 1 is computing the mean of the derivatives. This is called the first moment, and beta 2 is used to compute exponentially weighted average of the squares, and that's called the second moment. So that gives rise to the name adaptive moment estimation, but everyone just calls it the ADAM optimization algorithm. And by the way, one of my long-term friends and collaborators is called Adam Coates. As far as I know, this algorithm doesn't have anything to do with him, except for the fact that I think he uses it sometimes, but sometimes I get asked that question, so just in case you're wondering. So that's it for the ADAM optimization algorithm. With it, I think you really train your neural networks much more quickly. But before we wrap up for this week, let's keep talking about hyperparameter tuning, as well as gain some more intuitions about what the optimization problem for neural networks looks like. In the next video, we'll talk about learning rate decay.